In Module 11, we will discuss rational exponents, radicals, and complex numbers. In Module 11, Section 1, our focus will be radical expressions and radical functions. Radicals are nothing more than roots, and so let's start by talking about square roots. The opposite of squaring a number is taking the square root of a number. And so the definition says the number b is the square root of a if b squared equals a. The principal square root of a non-negative number is its non-negative square root. The principal square root is written as the square root of the number, or in this case we say square root of a. The negative square root of a is written as negative square root of a. Each number will have a principal square root as well as a negative square root. Let's try practicing with the definition we saw before and finding each square root. And so basically what we're trying to find is the number raised to the second power that will give us the number underneath the square root. So we want to know what number raised to the second power will equal 49. And in the next section, we'll look at a shortcut for finding this, especially with larger roots. But here you should be able to use a calculator or just use simple multiplication facts to find the answer. We know that 49 is the same thing as 7 times 7, so 7 squared equals 49. And for that reason, we would say the square root of 49 equals 7. The same thing can be said with fractions. Essentially, you're looking for the two identical factors in the numerator and the two identical factors in the denominator. We know that 25 is 5 times 5, so the square root of 25 is 5. The square root of 16 is 4 times 4, or 4 squared, so the square root of 16 is 4. So the square root of 25 over 16 is 5 over 4. Now when a negative sign is written in front of the square root, that negative sign will carry to the answer because we want the negative square root instead. We still work the square root of the number the same exact way. We want to know what number to the second power will give us 4. We know that 4 can be rewritten as 2 times 2, or 2 squared. So the square root of 4 is 2. And because we wanted the negative square root, the answer will be negative 2. We can also apply the same rule to a variable expression. Here we have 9x to the 4th power. Well, we know 9 is 3 times 3. If we want to use identical factors to get x to the 4th, we could rewrite that as x squared times x squared. So what we have is 3x squared times 3x squared, or 3x squared to the second power equals 9x to the 4th. So for that reason, using the definition from the last page, or 2 slides ago, we see that the square root of 9x to the 4th is 3x squared. Sometimes we'll be asked to approximate a square root. There is a way to do this without the calculator, but we're not going to learn it in this class. And so anytime you're asked to approximate or find a square root and the directions tell you to round, we're going to put this number in the calculator and round to whatever decimal place you're asked to find. So in this example, let's just round to 3 decimal places. We get 2.236. Just like the square root, the cube root of a real number a is defined as, we still use the radical sign, but instead of not having a number or the number being 2, the cube root is represented with the index of 3. So the cube root of a equals b only if b cubed equals a. So we want to find what number raised to the 3rd power will equal the number underneath the square root. So I'm going to write the first few cubes in hopes that you will write these in your notes and be able to use them for the next few problems and possibly the problems in your homework. 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125. We could keep going. That should be enough to start working most of the problems. Sometimes you might find numbers that are higher than 125, but for the most part this will work. Plus in the next section we'll have a shortcut. So let's try to find each cube root. We can use the cubes that were listed on the last page to find all of these cube roots. We have the cube root of 27, and just like we saw from the last page, 3 to the 3rd power equals 27, so the cube root of 27 is 3. The cube root of negative 125, as long as the root is odd, and in this case the index is 3, so we have an odd root, it is perfectly okay to have a negative number underneath. Remember, if I have negatives, one negative value, it's negative. 2 negatives that are being multiplied, it's positive. 3 negatives would give me another negative value. So it makes sense that we would have a negative underneath, or it's perfectly okay to. If we go back to the last slide, we see 5 raised to the third power is 125. So negative 5 raised to the third power will give us negative 125, and our answer is negative 5. In part C, we evaluate the numerator and denominator simultaneously. The cube root of 8, 2 to the third power is 8, so the cube root of 8 is 2. The cube root of 125, we just found that, is 5. So the cube root of 8 over 125 is 2/5. In part D, we work this in a very similar way that we would have with the square root. We know the cube root of negative 8. If the cube root of positive 8 is 2, the cube root of negative 8 is negative 2. Now, when trying to find x to the 9th and its cube root, we're trying to find some x power raised to the third power. Well, remember when we have multiple powers, we multiply, so we want to find 3 times what? That would be 3 times 3 gives us 9. So x cubed to the third power equals x to the 9th. So the cube root of x to the 9th is x to the third power. Other roots can be found as well. We would say the nth root because we could put whatever number in for n that we chose to. We would write a little n for the index instead of a 2 or a 3. It could be a 4th root, 5th root, and so on. And in that case, we would need our number raised to that power. If it was a 4, we would need something raised to the 4th power, 5th power, and so on. And it would need to equal what was underneath the root. So for example, if I have the 6th root of 64, we have to try to find some number raised to the 6th power that would equal 64. And if you play around long enough, you would find 2 to the 6th power equals 64. So the 6th root of 64 equals 2. For the next example, we have the 5th root of negative 32. It's okay to have a negative because we have an odd index. If we tried 2 to the 5th power will give us 32, so negative 2 to the 5th power will give us a negative 32. So the 5th root of negative 32 is negative 2. And make sure our exponent matches the index. And we've used 2's and negative 2's twice already. Let's try to use 2 again with a different index. We have the 4th root of negative 16. Here's a problem though. Unlike the first 2 times, we saw the negative underneath the radical sign. Here we have an even index. And anytime we have an even index, we cannot have a negative underneath the radical because that gives us a not real solution. Now, before this module is finished, you will know how to deal with not real solutions, but right now it is sufficient to say it's not real. Let's try the next 2 examples. We want to simplify the following, assume that all variables represent positive numbers. Now here's where we're going to look at the shortcuts we can use in order to find roots other than square roots and possibly cube roots. The first thing we need to look at is the index. And the index tells us how many factors of the same number we need before we can pull that number out of the root, whether it be a 4th root or a cube root and so on. And so to find that number of factors, we make a factor tree. We take 16 and divide it by whatever prime numbers we can. So we start with 2. That's 2 and 8. 8 is 2 and 4. 4 is 2 and 2. So when we look at the prime factorization of 16, we have 2 times 2 times 2 times 2. Once we find the prime factorization of a number, we want to circle the number of factors indicated, the number of identical factors indicated by the index, the number we circled at the very beginning. So we need 4 identical factors, and we just happen to have 4 2's. So when we're dealing with the number, the 4th root of 16, we treat this like it's one number. That group represents just 2. So the 4th root of 16 is 2. Now let's talk about the exponent on the variable. When dealing with the variables, you take the exponent of the variable and you divide it by the same index that we use to find how many factors need to be in the group. So 4 divided by 8 is 2. Do our long division. You may not have done this in a while. We have 0 remaining. We have no leftovers. The quotient of our long division tells us how many factors we are going to pull out of the root. So we have 2 factors of x we're bringing out from outside of the root. That's x squared. And the remainder tells us how many factors of x are still underneath the root. Because at 0, there's nothing left underneath the root. We had no extra factors from our prime factorization of 16. We have no remainders from our long division with the variable. So the 4th root of 16x to the 8 is 2x squared. Let's try the next example. The first thing we need to look at is the fact that we have a negative on the outside and a negative on the inside. It's okay that we have a negative on the inside because we have an odd root, but with an odd root, we can move our negatives inside and outside as much as we want to. So two negatives beside one another here will actually turn this into a positive root. So we have the fifth root of 32, a to the fifth, over b to the 15th. If we go through the same process we did on the last example, we first make the prime factorization of 32, which you can use a factor tree. I'm just going to write the prime factorization. It's 2 times 2 times 2 times 2 times 2. The index tells us we need 5 identical factors to form a group. Here we have 5 identical factors. They form one group of 2's. So the fifth root of 32 is 2. We now look at the exponents of the variables, and we're going to do long division. We take the exponent of 5 and divide it by the index. 5 divided by 5 is 1. So we bring out one factor of a, just a, no remainders, over, because b to the 15th is in the denominator. Let's also do long division. 15 divided by 5 is 3. So we bring out 3 factors of b, or b cubed. There were no remainders. There were no leftover factors in our prime factorization. So 2a over b cubed is the answer.